Hi everyone, here's Wenze. Today we will explain the Android project using NetGDM, XGBoost, random forest, and the SVM model to find the higher F1 score to predict the stroke. The first step in building an effective stroke prediction model was preparing the refining our dataset to enhance model performance. We begin by examining the dataset for missing values, duplicates, and incorrect data types. We can see there is no missing values and duplicate values in the trained data. Once the dataset was cleaned, we access the distribution and observe a significant imbalance between the stroke and non-stroke cases. To address this, we applied SMOT in later code to generate the synthetic data point for the minority class. Without this step, our models would have likely been biased towards predicting the majority class, leading to poor recall for the stroke cases. By resampling the data, we ensure that the model could learn meaningful patterns from both cases. Next, we focus on outliers. You can see the outliers graphs. We use visualization to deal with outliers. Next, we perform the feature scan in the standardized numerical features. And since the different features have different magnitude, we apply the minimax scaling to normalize all numerical variables within a range of 0 to 1. This step was especially important for the models like SVM, which can be sensitive to variations of features magnitude. For category variables such as gender, work type, and the smoking status, we use one-hot encoding to transform them into columns for each category, allowing models to interpret category data without assuming an inherent or ordinal relationship between categories. To enhance the predictive power, we introduce new features based on the domain knowledge. We categorize the age into risk groups, divided BMI into standard weight categories, and grouped glucose levels into distinct ranges. This transformation will allow models to better capture nonlinear relationships that may not be evidenced in raw numerical values. Following features engineering, we apply correlation analysis. Following the features engineering, we apply correlation analysis to filter out irrelevant features. Using the correlation matrix, we examine the relationship between all features and target variables, selecting only those with an absolute correlation of greater than 0.05 with stroke. And any features with low correlation were removed to reduce noise and prevent unnecessary complexity in the model. With our dataset properly balanced, normalized, and refined, we proceed to model training. Let's welcome Qingqing to explain the model training.
So after completing the data pre-processing, we train and evaluate the multiple classification models to identify the most effective one. We implemented 3 tree-based models like GBM, XGBoost, and the random forest. To optimize these models, we use Optuna, an automated hyperparameter tuning framework, which help us fine-tune the learning rate, maximum the tree depth, number of the estimators, and the feature sampling ratios. Each model was evaluated using the stratified k-fold cross-validations. Here is a code, and with the F1 score as a primary metric to balance the precision and recall in handling the imbalanced datasets. After the hyperparameter tuning, we proceed with the training and cross-validation. We also apply the SMOD with the sampling strategy of 0.5, ensuring that the number of synthetic stroke cases generated was half the number of non-stroke cases. This approach prevented the excessive oversampling while maintaining sufficient representation for the stroke cases in the dataset. Next, we analyze the feature importance here. Here's the code. Using the best performing model, we extracted feature importance values, ranked features, and applied a 75% higher threshold to fill out the less important ones. We then retained the model on the selected features to improve the generalization. Once the training was completed, we assessed model performance. Here is the outcome. For the light GBM achieved an F1 score of 0.2749, indicating the moderate performance. XGBoost significantly underperformed with an F1 score of 0.0154, suggesting that it struggled to handle the dataset effectively. Random Forest outperformed both with an F1 score of 0.2896, making the best performing model at this stage. So given its superior performance, we initially selected the Random Forest as our final model. To further explore the potential improvements, we introduced an SVM classifier as an alternative to tree-based models. SVM was optimized also use Optina. Here's a code, and where we tune the regularization parameters, kernel type, and gamma values for nonlinear kernels. After hyperparameter tuning and the trainings, the SVM model produced an exceptionally high F1 score. Here is a score which is 0.7408, significantly outperforming all previous models. However, when we submitted the SVM-based prediction to Kaggle, the evaluation score was unexpectedly low. This discrepancy indicates a strong likelihood of overfitting, while the model performed well on our resampled training data. If failed to generalize to the unseen test data, this outcome reinforced the importance of not only achieve the high cross-validation scores, but also ensuring that the model maintains real-world applicabilities. Given this issue, we concluded that the random forest model, despite having a lower F1 score than SVM on our internal evaluation, was more reliable and generalizable. As a result, we finalized the random forest as our chosen model for submission, as it provided the best balance between the performance and the generalization ability. Thank you.